Welcome to the Explainer. Imagine your upcoming Cambridge computer science exam as a barren wasteland, a Mad Max Fury Road filled with tricky questions, time traps, and command word ambushes. Today, we are going to navigate that wasteland and claim your grade treasure. I've analyzed thousands of real Cambridge past papers across syllabuses 0417, 0478, 2210, and 9618, and I constantly see two types of students. First, there's Alex. Alex overloads every answer with raw computer science facts, but provides absolutely zero analysis. Then there's Sam. Sam rushes, completely misses the command word requirements, and writes vague, generic answers. Today, we are going to look at their flawed answers, covered in red pen marks, and show you exactly how to transform them into top-tier A-star responses. Let's dive right into data representation mastery. Here's our roadmap for today's session. We'll be covering base number systems, binary shifts and errors, digitizing media, storage calculations, compression methods, and finally, the examiner's perspective. Let's get straight to it. Section 1. Base number systems, the digital foundation. To conquer this exam, you must understand computing at its bedrock. Every single complex system fundamentally relies on binary. Why? Because those ones and zeros perfectly correspond to the physical on and off electrical states within a computer's hardware. Now, look at this table. You see binary is base 2, denary is base 10, and hexadecimal is base 16. Now, our student Alex memorizes this table perfectly. But when an exam question asks, explain why hexadecimal is used instead of binary, Alex just writes, hex is base 16 and uses letters A through F, red pen, 0 marks. Why? Because Alex didn't answer the command word explain why. Alex just stated a fact. To secure marks, you need to understand that dealing with long strings of ones and zeros is exhausting and error-prone for humans. Hexadecimal is a tool. It simplifies those unwieldy binary numbers into shorter, much more manageable codes for us humans to read and debug. A classic exam application of this is the MAC address. A media access control address identifies a device on a network through its network interface card, and it uses a hexadecimal format just like the one on screen. Now, our other student, Sam, sees a question asking to identify uses of hexadecimal. Sam rushes and just writes MAC addresses. 1 mark. But if the question is worth 3 marks, Sam just left 2 marks stranded in the wasteland. This is where we introduce the strategy reveal. Cambridge uses specific assessment objectives, or AOs. You need to decode the command word and use the Peel framework: point, evidence, explanation, link. For a 3-mark question on hex, your point is that it's used for MAC addresses. Your evidence is the format, showing the manufacturer and serial number. Your explanation is that hex makes this long address easier for network technicians to read and less prone to transcription errors. Do you see the difference? Structure is your armor. Section 2. Binary shifts and errors, calculating limits. We know how to represent positive numbers, but how does the computer handle negative values when all it knows is 1 and 0? It uses 2's complement notation. In an 8-bit register, the leftmost bit, the most significant bit, becomes a negative value, specifically -128. Let's look at the step-by-step mathematical process to convert a positive denary number, like 67, into a negative 2's complement binary format. First, you write out the positive binary value. 64 plus 2 plus 1 gives us 01000011. Step 2. Invert every single bit. Every 0 becomes a 1, and every 1 becomes a 0. That gives us 10111100. Finally, step 3, simply add 1 to that inverted number. Our result is 10111101. This is exactly how top students structure their mathematical answers. They don't just put the final binary string. They show the examiner every single transformation step. But you have to be aware of the limits of the hardware. When calculations push past what a register can physically hold, chaos ensues. Imagine adding 2 large 8-bit numbers where the binary carry operations generate a 9th bit on the far left. There was literally no physical space for a 9th bit in an 8-bit register. The system drops it, leaving a completely incorrect value. This is called an overflow error. Now, before we continue and break down exactly how to explain this in an exam using the PEL framework, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the strategy. If you get a question on overflow errors, apply PEL. Point, the calculation exceeds the register size. Evidence, a 9th bit is generated in an 8-bit system. Explanation, the hardware cannot store the extra bit, causing it to be dropped. Link. This results in an inaccurate calculation known as an overflow error. That is a guaranteed full mark answer. Section 3. Digitizing media, text, sound, and images. Let's move from abstract numbers to how a computer digitizes the real world. This is where we begin the transformation phase. Watch how those red pen marks turn into green check marks. Let's look at images first. Bitmap images are a grid of pixels, and each pixel is a binary number. The key definition here is color depth, the number of bits used to represent each possible color in a bitmap image. Alex gets a question. Explain the effect of increasing color depth. Alex writes, color depth is the number of bits for colors. More bits mean more colors. It makes the file bigger. The examiner size. That's a low-level answer. Let's use the computer science success blueprint to rewrite this. The blueprint says we need to explain the mechanics. The rewrite, increasing color depth, for example, from 3 bits to 8 bits, exponentially increases the number of available colors from 8 to 256. This significantly improves the image realism and quality, but because more bits are required per pixel, the overall file size will increase proportionally. Boom, green check marks across the board. It's a similar story with analog sound waves. To digitize sound, the waves must be sampled at regular intervals. Look at these two graphs on screen. The top one uses an 8-bit sampling resolution. There are very few vertical steps to measure the amplitude, so the digital reading often falls between the lines. The computer is forced to round the values, which destroys accuracy. But look at the bottom graph. By jumping to a 16-bit sampling resolution, we have vastly more distinct values. The digital representation maps to the analog wave incredibly accurately. Sam gets a question on this and writes, 16-bit sounds better. Red pen, 0 marks. Sam missed the entire technical explanation. Let's transform it. Increasing the sampling resolution from 8 to 16 bits provides more discrete values to represent the sound's amplitude at each sample interval. This reduces quantization errors and creates a much more accurate digital representation of the original analog sound wave. That is how you secure the grade treasure. Section 4. Storage calculations measuring data. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's talk about the math that trips everyone up. Calculating file size is a critical exam skill. The formula is image file size equals the resolution, which is the total number of pixels, multiplied by the color depth in bits. But the exam won't stop there. You have to convert bits to bytes by dividing by 8, and then often into kilobytes, megabytes, or gigabytes by dividing by 1024. It is time for our interactive workshop. I want you to look at this complex data source on the screen. This is a classic high-mark exam question. Challenge 1, the data scan. You have 60 seconds on the clock in your head. A camera has an array of 2048 by 3072 pixels, a 32-bit color depth, and 64 GB of memory. How many images can it store? Don't panic, rely on the system. Step 1, multiply the pixels by the depth. 2048 times 3072 times 32. That's your total bits per image. Step 2, divide by 8. That gives you roughly 25.1 million bytes per image. Step 3, find the total bytes in 64 gigabytes. Multiply 64 by 1024 3 times. That gives you a massive 68.7 billion bytes. Finally, divide the total memory by the size of one image. The answer is 2,730 images. If you meticulously write down every single one of those steps on the exam paper, you are golden. Section 5, Compression Methods, Shrinking the Data. Welcome to Challenge 2 of our workshop, Find the Flaw. I'm going to read you a sample paragraph about this table on compression, and I want you to spot the sentence that loses marks. Here we go. Compression shrinks data. Lossy compression removes unnecessary data permanently, so the file is much smaller, like a JPEG. Lossless compression means no data is lost, and it shrinks the file by removing empty spaces. The original can be perfectly reconstructed. Did you spot the flaw? It's the phrase, removing empty spaces. That is a classic SAM mistake. Vague terminology. Lossless compression doesn't remove empty space. It uses encoding algorithms to find patterns and compress data without losing a single bit of information. You must clearly distinguish that lossy permanently discards data, while lossless perfectly preserves it using clever math. Let's look at that clever math.
Run length encoding, or RLE, is a prime example of lossless compression. Now it's time for Challenge 3, speed writing. You have 30 seconds to look at the slide and mentally draft a perfect peel paragraph. Go. Notice how RLE works on this pixel grid. Instead of saving data for every individual pixel, it looks for adjacent identical items. Instead of writing white, white, white 6 times, it simply codes 6 times white. Time's up. Here is your perfect paragraph. Point. RLE reduces file size without data loss. Evidence. It replaces repeating adjacent data elements with a single value and a count. Explanation. This heavily reduces the number of bytes required to store areas of identical color, cutting file size by over 50% in some cases. Link. Therefore, the original image can be perfectly reconstructed upon opening. Master this, and you master the exam.
Section 6. The examiner's perspective. Acing the exam. We are entering the final stretch. This is where we present the complete computer science answering system. Rule number 1. Command word decoding. Look at these 2 answers explaining lossy compression. The low-level answer, lossy means data is lost permanently, completely fails to decode the command word explain. It just gives a basic definition. The high-level answer follows rule number 2, peel framework application. It explains the mechanism, eliminating unnecessary data. It explains the results, yielding much smaller files. And it provides evidence, giving JPEG as an example. This isn't just about knowing the facts, it's about packaging them exactly how the examiner's mark scheme demands.
Rule number 3 is the time management matrix, which includes strategic calculation. Listen to this direct quote from a Cambridge examiner. The calculation shows all of the steps. If you make any errors in your calculation, by showing all steps, you could still gain a good mark even if your final answer is incorrect. This is the ultimate exam hack. Writing your math logic line by line is your grade insurance policy. If Sam rushes, makes a calculator error, and just writes down the wrong final number, that's 0 marks. If Alex writes down the formula, plugs in the numbers, converts bits to bytes, but messes up the final division, Alex still walks away with 3 out of 4 marks. Never skip the steps.
And speaking of skipping steps, let's talk about the zero fill trap. If the question commands you to write a denary number as an 8-bit binary number, you must follow those exact parameters. Look at the low-level practice on screen. The student wrote 101100. Yes, mathematically, that equals 44, but it is only 6 bits long. The command word was 8-bit format. The high-level, correct practice is to infill those empty spaces on the left with leading zeros, making it 00101100. Missing leading zeros is the fastest way to bleed easy marks on a Cambridge paper. Don't let a lack of formatting ruin your grade treasure. Finally, you must eliminate vague terminology from your vocabulary. Read this examiner note closely. The statement, uses up less space, gets 0 marks. Why? Because the word space is meaningless in computer science. Are we talking about physical desk space for the monitor? The space on your hard drive? The RAM? You must be precise. If you write reduction in storage space requirements or consumes less secondary memory capacity, you lock in the points. Train yourself to speak the technical language of the syllabus, and you will never fall into the vague terminology trap. So, as we wrap up this explainer, I want to leave you with a final thought to ponder. If every vivid pixel and crisp soundbite you've experienced in this session is merely an illusion, built entirely from a highly compressed ones and zeros, what invisible data is your own device permanently discarding right this very second just to stream it to you? You now understand the invisible math powering that process, and more importantly, you possess the strategic blueprint to prove it to any examiner. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.